Alright, so today I want to prove that if we have a normally distributed random variable according to some mean mu and some variance sigma squared, I want to prove that a constant multiplied by this normal random variable will also follow a normal distribution with mean c times mu and variance c squared sigma squared for some non-zero constant. And intuitively, you can imagine this is true. If I just multiply a constant by my mean, that will shift my distribution somewhere. And if I multiply some value, my variance might spread more. But we're going to actually do the all of the math to actually show this is true. And even though it's a fairly simple result, the math behind it is fairly technical. So the approach I'll be using is to prove by MGFs. So basically what we're going to do is we're going to first derive the distribution of the transformation multiplying a constant. And then once we have that distribution, we're going to derive the moment generating function and then show that this moment generating function is in fact represents a normal distribution, which we can then extract the parameters. So I'm not sure how long it will take exactly, but this might be a little long. So first, let's begin. So assume we apply some linear transformation, y equals c times x. And the way we can derive this distribution, there's a number of ways we can do this, but one common way is to look at cumulative distribution functions, because recall that the derivative of a cumulative distribution function is the probability density function. And so if we look at the cumulative distribution function of y less than or equal to x, this is cx, and forgive my my writing skills. I'm freehanding with the mouse, which is not the easiest thing in the world. So this is probability of cx less than x, and as you can see, x less than or equal to x over c, and again c is non-zero. So this is the cumulative distribution function fx of x over c. And now to get the density function, we could just basically differentiate this with respect to x. Notice that we have not just an x term in here. We're dividing by this constant, so we'll have to use the chain rule. And so we'll take that, take the derivative of the inside, and then the derivative of the CDF itself is the density function. So this is fx of x over c. And just one minor detail, this inside or this outer derivative will actually be the absolute value of c. The easy explanation is that your density can't be negative, so you just want the positive result, because if we evaluate a point on a probability density function, it can never be negative. That's the easiest explanation I can give. There's a bit more detail to go into there, but that specific topic is a bit out of scope for now. But basically, this is 1 over the absolute value of c times the density. So just make it a little bit more clear here. All right, so this is the probability density, or this is the distribution of multiplying a constant by some random variable. And again, in our case, our random variable is a normal distribution. So let me, how do I clear this? I haven't used Microsoft Whiteboard in a while. It's not very intuitive. All right, whatever. I'll just do this. It's not the greatest thing ever, but whatever. Okay. So now we have our distribution. 1 over the absolute value of c, and just to make it simpler, let's just assume that c is positive. We just scale it by a positive constant, and it doesn't have to be positive, but just to get rid of this absolute value, let's just look at the specific case of being greater than 0. So that way I could just write c here, and then this is just the normal definition, so sigma over root 2 pi e to the, man, freehanding this is kind of difficult, e to the, so now we have x over c minus mu squared over 2 sigma squared. Again, apologies for my terrible writing. So this is the distribution of that transformation. And, you know, from here, it's not immediately obvious, but to fully show, and you probably could figure out some type of algebra to figure it out from here, but I'm going to do the full treatment. And so to derive the MGF, we're going to take the expected value of this raised to tx, and so this will give us the integral, so 1 over c sigma root 2 pi, and then we have the integral from negative infinity to positive infinity of e to the tx times e to this whole nonsense with respect to x. And so I'm just going to focus on the exponent portion here. So, well, if we multiply these two exponents, then this becomes basically e to the tx plus, or I guess minus, this whole expression here. So let's actually go off to this side over here and kind of simplify this a bit. So we have tx minus x over c minus mu squared, and all of this is over 2 sigma squared. So let's just take a look at this expression first. So this will be x squared over c squared minus, and then we have x over c times mu negative mu times x over c. So this is 2x mu over c plus mu squared. And again, this is all over 2 sigma squared, so I'll just write it like this. This is 2 sigma squared c squared 2 sigma squared c 2 sigma squared. And then at the end we have tx over here. So we have tx minus, so minus all of this, but this is in brackets, so this will be minus, plus, and then minus, how do I erase? And that's because we're subtracting this in parentheses. So we just distribute that subtraction, and we get tx minus this plus this minus this. And so now we only want to consider the x terms, and you'll notice that this is a constant term. And again, keep in mind that all of this is basically raised to e, and so we can take out this portion outside of the integral. And so let's do 1 over c sigma root 2 pi e, and then we're going to take out this constant, e to the negative mu squared 2 sigma squared, and times the integral from negative infinity to positive infinity. And then just one more thing real quick. So we got rid of this constant. Now I just want to consolidate this x term here. I'm actually going to rewrite this a little bit. So we have negative x squared over 2 sigma squared c squared. And then if I factor out x, this becomes t plus 2 mu over 2 sigma squared c. So now let's bring that down here. So we have e to the negative x squared over 2 sigma squared c squared plus x t plus 2 mu 2 sigma squared c dx. Alright, so now you might be kind of scared of this integral. It's like, oh great, I have an e to the x squared term, there's this e whatever, but there's actually a convenient form we can use to integrate this. Since we're integrating from negative infinity to positive infinity, we can use a Gaussian integral. And a Gaussian integral, at least one of the generalizations that we can use is, if you have an integral from negative infinity to positive infinity of e to the negative, and then you have a degree 2 polynomial, so ax squared plus bx plus c, with respect to x, this is pi over a, or sorry, root pi over a, times e to the b squared over 4a, and then I think it's minus c. The c term I don't exactly remember, but it doesn't matter because we don't have a constant term anyways. So this is what we're going to be using. So in our case, let me see if I can move this. Oh, that's weird. Okay, we'll just move that over there. All right, so in our case, a and so remember that this whole thing is negated. So in our case, a would be positive 1 over 2 sigma squared c squared, because a is already negative, and if you distribute the negative here, negative a is positive in this case. But b, on the other hand, we have a positive term here, but according to this it would be negative, but it doesn't matter because we're going to be squaring it anyways. So b is equal to negative t plus 2 mu, or we can just cancel out the 2. We'll do mu over sigma squared c. That's supposed to be sigma. And so b squared is just, I'm just going to ignore the negative because it's not going to matter. Mu over sigma squared c times this again. Oh, sorry, this is not t squared. That's just t. So this is t squared plus, and then you get mu t, so this becomes plus 2 mu t over sigma squared c plus mu squared sigma squared c. That's supposed to be, yeah, that's a C, okay. Sometimes I can't even read my own handwriting, so again, apologies for the bad handwriting. It's very hard to write properly with a mouse. Okay, so this is A. So let's just do 1 over 4a real quick. So 1 over 4a will be multiplying this by 4 and then inverting it, which will be just flipping the numerator and denominator. So this will be 2 sigma squared c squared over 4. And so b squared over 4a equals 2 sigma squared c squared over 4 times t squared plus 2 sigma squared c squared over 4 times 2 mu t over sigma squared c plus 2 sigma squared c squared over 4 times mu squared over sigma squared c. Alright, so now let's just continue. So this is sigma squared t squared, and then the 2 and 4, sorry, I forgot the c here, sigma squared c squared t squared over 2, because the 2 and 4 divide. And then here, so the sigmas cancel out. This 2 times 2 divided by 4 cancels out. One of the c's cancel out, so we just get with 1, and so we get mu t, or I'm going to write it like this instead, t mu c, and then the sigma cancels out. This divides into 2, so we get plus mu squared c over 2. And wait, I feel like there's one thing that I messed up here. Okay, yeah, this is supposed to be c squared, because I didn't multiply this portion. Oh, actually, this is supposed to be to the 4th, sorry. Yeah, I did not distribute this correctly. So that's sigma to the 4th c squared. I just didn't multiply that properly. So let's see. So sigma to the 4th c squared. So, okay. With that in mind, this last problem, so sigma squared over sigma to the 4th. Okay, here, let's just do this. We'll just write it out fully. That way it's kind of easier for me to visualize. So we have 2 sigma squared c squared mu squared over 4 sigma to the fourth c squared. So the c squareds cancel out. This cancels out, and this becomes squared. And then the 2 cancels out, this becomes 2. So this will become mu squared over 2 sigma squared. So let's just replace that. All right. And then finally the last portion, the root pi over a. This is root pi over, and then we have 1 over something, so that something moves up to the top here. So we have root pi times whatever a is, so 2 sigma squared c squared over here. So root pi 2 sigma squared c squared. And so you can see that this just becomes root 2 pi times sigma times c. And so finally, this integral, let me just copy this. So this integral here, this equals, so we'll have 1 over c sigma root 2 pi e to the negative mu squared over 2 sigma squared times the result of this integral, which is root, or I'll write it this way, c sigma root 2 pi times e to the t squared sigma squared c squared. So we're just copying this portion right here, this whole expression, over 2 plus t mu c plus mu squared over 2 sigma squared. All right, and as you can probably see, when we multiply these two, this constant and this constant are equal, so these actually cancel each other out. And then we are left with e, and notice that when you multiply, again, when you multiply exponents with the same base, you can add their exponents. So this is negative mu squared over 2 sigma squared, and this is positive mu squared over sigma squared. So these two terms actually cancel each other out as well. And you're left with e to the t squared sigma squared c squared over 2 plus t mu c. And at first, this might not seem like much, but the MGF of a normal random variable, let's just say x, if x is normal. So if x is distributed with mean mu and variance sigma, the MGF is e to the t squared sigma squared over 2 plus t mu. And look here, if we look at t squared here, and t, so in this case mu equals mu, or sorry, here, let me do this instead. So if we call this like sigma prime and mu prime, just to kind of translate them, so mu prime here equals mu c, because we have t times mu prime, t times mu c, and then sigma squared prime, or sigma whatever, the variance, or I guess it doesn't have to be sigma, just this constant that we're multiplying t squared by, we have sigma squared c squared over 2. So you can think of, or I guess you could say, think of the variance sigma squared here, sigma squared prime, whatever. This is sigma squared c squared. And so these are the same two moment generating functions, which implies that they're the same distribution, except we have scaled that distribution by the factor of c. And so this implies that the distribution of this variable here, or this transformation, is a normal distribution with mean mu c and variance c squared sigma squared if x is distributed according to mu and sigma squared. And so that concludes our proof. It's just under a half hour almost. So hopefully found this useful or insightful. Hopefully I didn't leave out anything that was confusing. But yeah, that's pretty much it.